Welcome to RadOnc Smart Review Physics Edition.
Today we're shifting gears a bit from external beam radiation therapy and getting up close and personal, well, with brachytherapy.
Exactly. We're going to take a really comprehensive look at treatments where the radioactive source isn't way off in a machine, but is
Yeah.
actually placed, inside or very close to the target tissue, delivering dose right where you need it most.
It's a really powerful technique, but it definitely comes with its own unique set of physics principles. We need to understand those.
Mm.
So we'll explore the different types of sealed radioactive sources used in modern brachytherapy. We'll delve into how we properly quantify their strength, how strong is this source,
Right.
in a standardized way.
Yeah, that standardization is key.
And then we'll meticulously unpack the fundamental framework used for calculating the dose around these sources, the TG43 formalism. Understanding TG43 is, well, it's non-negotiable for safe and effective brachytherapy. You just have to know it.
Absolutely. It's foundational knowledge for anyone practicing radiation oncology, whether you're doing, say, LDR prostate seeds or HDR GYN tandems. And crucially, it's incredibly high yield for your board exams. They love asking about this stuff.
They really do.
So grab your favorite beverage, maybe not a radioactive one, though, and let's get started.
Right. So brachytherapy fundamentally relies on using a variety of sealed radioactive sources. These aren't just, random radioactive materials. They're specifically chosen isotopes, manufactured into small encapsulated units.
So beard units.
And each one has unique physical properties. Those properties dictate their clinical application. Choosing the right one for a given clinical scenario, the tumor type, its size, location, how close it is to organs at risk, that choice is absolutely critical for effective treatment planning and delivery.
I kind of like to think of the different sources as specialized tools in a brachytherapy toolbox. You need to know which tool, which isotope is the right one for the specific job, the clinical scenario, and target volume.
That's a good analogy.
And you mentioned boards. Yeah, you absolutely must know the half-life, T1/2, and average energy, AVGE, of the common players. I mean, these values are tested frequently because they directly influence clinical decisions, safety protocols, everything.
Definitely. So let's categorize them first by their emitted radiation energy. This energy is really a primary determinant of how far the photons or particles will travel and deposit dose in tissue.
Right, so higher energy photons generally mean more penetration, deeper dose, while lower energy photons and betas mean the dose stays more localized, right? Drops off faster.
Exactly. First up, we have the high-energy gamma emitters. These are sources that emit photons directly from the nucleus during radioactive decay, with an average energy typically greater than, say, approximately 300 kilo-electron volts.
Okay, so these photons have enough energy to penetrate further in tissue compared to the lower energy sources. That makes them suitable for applications where you need to deliver dose over maybe a larger volume or treat larger tumors or deliver dose from a bit of a distance within a body cavity, like using intracavitary applicators for GYN cancers.
Precisely. And the most common source in this category today, arguably the undisputed current king of high dose rate, or HDR, brachytherapy globally, is iridium-192, 192 IR.
Oh yeah, you see iridium everywhere in HDR. It's incredibly versatile, used across a wide spectrum of treatment sites, right?
Absolutely.
GYN, brachy, interstitial breast, APBI, prostate HDR, head and neck implants, sarcomas. The list just goes on. And its flexibility, the fact it can be made into wires or tiny pellets, makes it adaptable to so many different applicator types.
And its physical properties are really key to its HDR use. Its T1/2 is approximately 74 days,
74 days, okay.
which is, a relatively short half-life. It means the source decays relatively quickly, so you have to replace it in the HDR afterlitter machine typically every, 3 to 4 months. Depends on the workload and the strength you need.
Right. And that decay also means treatment times creep up over the source's life.
Exactly. The average gamma energy is approximately 380 kilo-electron volts.
380 kilo electron volts.
So that energy is high enough to provide sufficient penetration for treating larger volumes or from those intracavitary positions, but it also has, let's say, reasonable shielding requirements compared to even higher energy sources like cobalt-60.
It's worth remembering historically, too, like before HDR became so standardized, iridium-192 was also used for low dose rate LDR temporary implants, usually as wires, right? Manually threaded through catheters.
That's right, yeah, before the afterloaders became common. Okay, next up, a source with significant historical importance, especially in LDR GYN brachytherapy. This is the one that largely replaced radium-226 for many years, cesium-137. 137 CS.
Cesium-137, you still see it referenced a lot, right? Especially in older literature or comparing new techniques, or maybe even on boards comparing properties to radium or iridium.
Definitely, its properties. T1/2 is approximately 30 years.
30 years, wow, that's long compared to iridium.
Very long. This longevity means its activity decays very, very slowly. That made it suitable for situations where, source management benefited from infrequent replacement,
Yeah.
mostly used in temporary LDR implants historically. Its long half-life, simplified inventory compared to shorter-lived isotopes. Though, obviously, iridium HDR has largely supplanted LDR cesium now.
And the energy.
Average gamma energy is approximately 662 kilo-electron volts.
Okay, significantly higher than iridium.
Yes, and that comes from the decay of its daughter product, barium-137 Miri.
And it's a fission product, right? Comes from nuclear reactors.
Correct. Extracted from spent fuel. While historically significant, and you might still find some sources around globally, it's much less common in modern clinical practice compared to iridium-192, especially with the big shift to HDR.
Makes sense. Okay, who's next in the high energy club?
All right, rounding out the high-energy group of commonly encountered sources, we have cobalt-60, 60CO.
Cobalt-60, this one really packs a punch, energy-wise. That high energy makes shielding a bit more challenging compared to iridium, I'd imagine.
It does. Properties. Cobalt-60 decays by emitting a beta particle, then almost instantly 2 gamma rays. Their average energy is approximately 1.25 mega electron volts, MeV.
1.25 mega electron volts. Okay, that's way higher than both iridium and cesium.
Significantly higher, and its T1/2 is approximately 5.3 years.
5.3 years, so longer than iridium, shorter than cesium.
Right. Now, while you might not see cobalt-60 as a primary brachy source in most standard clinics anymore, HDR is mostly iridium. You absolutely find this isotope in dedicated radiotherapy units for stereotactic radiosurgery, most notably gamma knife machines.
Right, gamma knife uses cobalt-60.
And some older HDR brachytherapy machines might also still use cobalt-60. Its high energy and that, intermediate half-life have different implications for shielding design and source replacement schedules compared to iridium.
Okay, so that covers the high-energy gamma emitters. What's next?
Now let's move to a fundamentally different group. Different in terms of their emitted radiation and how they interact with tissue. These are the low-energy photon emitters. Their average energy is generally less than about 50 kilo-electron volts.
50 kilo-electron volts. Okay, so much lower energy. And you said photons, but these aren't gamma rays from the nucleus like the others?
Correct. Typically, these sources decay via electron capture. That process leaves the resulting atom in an excited state, and as electrons rearrange themselves to fill that inner shell vacancy, characteristic X-rays are emitted.
Ah, so electron capture leads to X-rays. Got it.
And the key characteristic of these low-energy photons, these X-rays, is that their dose drops off very rapidly in tissue. Super steep fall-off.
And that rapid dose fall-off isn't just geometry, right? It's how they interact.
Exactly. It's significantly due to the way these low-energy photons interact with biological tissue. And this property makes them ideally suited for permanent seed implants, like for prostate brachytherapy.
Right, because you want a really high conformal dose right in the prostate, but you desperately want to spare the rectum, bladder, urethra right next door. That steep fall-off is perfect for that.
Precisely. The most commonly used low-energy source worldwide is iodine-125, 125I.
Iodine seeds, yeah, very common for LDR prostate permanent implants and also for eye plaques, right? Treating ocular melanomas.
Correct. Used extensively in both its properties. T1/2 is approximately 60 days.
60 days, 2 months.
Yep, so its activity reduces by half every 2 months. Over about 10 half-lives, so roughly 600 days, less than 2 years, its activity decays to almost nothing. It effectively delivers the vast majority of the prescribed dose within that first year or so.
Okay. And the energy?
Average energy is approximately 28 kilo-electron volts. 28 kilo-electron volts.
Wow. Okay, that is low energy.
And that low energy is precisely why it has that very rapid dose fall-off in tissue. It's because of prevalent photoelectric absorption at that energy.
Photoelectric effect really kicks in there.
It really does. Now, because of this low energy, you still need careful handling and shielding, although standard lead shielding is very effective. But the clinical use in permanent implants means the shielding considerations shift more towards patient release criteria and personnel handling after the implant, rather than massive room shielding during the procedure.
Makes sense. Okay, who else is in the low energy seed category?
Another very popular choice for LDR permanent prostate seeds is palladium-103, 103 PD.
Palladium. Right, often chosen maybe when a faster dose delivery is wanted, compared to iodine.
Exactly. Sometimes clinically advantageous, depending on, say, Gleason score or other factors, suggesting a more aggressive tumor where you want the dose delivered more quickly.
Okay, properties for palladium.
T1/2 is approximately 17 days. 1-7.
17 days. That's much shorter than iodine's 60 days.
Significantly shorter. It delivers its total dose much faster, most of it within the first couple of months after implantation. Its average energy is approximately 21 kilo electron volts.
21 kilo electron volts, even lower than iodine.
Slightly lower, yes.
Hmm.
And that generally translates to an even shorter range and potentially an even steeper dose fall off in tissue compared to I-125. That can be beneficial if critical structures are extremely close to the target and you need the absolute maximum dose gradient.
Okay, so iodine and palladium are the main two low-energy seeds. Any others we should know?
There's a third low-energy seed option you might encounter, also used for LDR prostate seeds. Cesium-131, 131CS.
Cesium-131, okay, how does that compare?
This one has the fastest decay among the commonly used seed isotopes.
Faster than palladium?
Yep. Properties. T1/2 is approximately 9.7 days. Call it 10 days.
Wow, very short. Delivers dose super fast.
Extremely rapidly. Essentially within the first month or so. Its average energy is approximately 30 kilo electron volts.
30 kilo electron volts, so slightly higher than iodine and palladium?
A little bit, yeah. So the choice between I-125, PD-103, and CS-131 for prostate seeds, it's a careful clinical decision, right? You're balancing the desired dose rate kinetics, how fast the dose goes in against the steepness of the fall-off, which depends on the average energy and tissue interaction, and you weigh that against prostate size, baseline urinary symptoms, Gleason score, physician preference, all that stuff.
But the common thread is that rapid dose fall-off, thanks to their low energies. That's the core advantage for all of them in permanent implants near sensitive structures.
Exactly. That steep gradient is key.
Okay. Any other source types?
Finally, we have a distinct class, pure beta emitters. These isotopes decay by emitting high-energy electrons, beta particles, not photons.
Electrons, or say charged particles. They interact really strongly with matter compared to photons, right? Which means they have a very short range.
Very short, finite range in tissue.
Yeah.
Exactly. This property makes beta emitters suitable for treating very superficial lesions or for highly localized internal delivery where that short range is actually beneficial.
Okay, what's the main example here?
The primary one encountered in modern therapy is yttrium-90, 90Y.
Yttrium-90, right, used in those liver-directed microspheres. SIRT, for liver tumors.
That's the main one, yes. Selective internal radiation therapy. Tiny glass or resin microspheres carrying yttrium-90 are injected into the hepatic artery. They preferentially lodge in the small blood vessels, supplying the tumor, because tumors often have increased vascularity.
So they deliver a high dose locally right to the tumor while sparing normal liver tissue somewhat because of that differential blood flow.
Exactly. Properties. Yttrium-90 is a high-energy beta emitter. Its average beta energy is about 0.94 mega electron volts, but the maximum energy is much higher, around 2.28 mega electron volts.
That sounds high energy, but you said the range is short.
It is. Despite that high energy per particle, the range in tissue is typically very short. The average range is only about 2.5 millimeters. Maximum range is maybe about 1 centimeter.
Okay, so very localized dose deposition. And the half-life?
U1/2 is approximately 64 hours.
64 hours, so about 2.7 days.
Right, so it delivers its dose relatively quickly, over maybe 2 weeks or so.
And that short range and relatively short half-life make it really conformal for that localized dose delivery within the liver where the spheres get stuck.
Precisely. You might also encounter other beta emitters, especially in ophthalmology, for treating superficial eye stuff, like pterygia or corneal neovascularization. Things like strontium-90, yttrium-90, or ruthenium-106, rhodium-106. These use applicators placed right on the eye surface, really leveraging that short beta particle range.
Got it. So a whole zoo of sources, each with its own niche.
Absolutely. Now, let's dive into something absolutely critical. This is key to understanding dose calculation and clinical application in brachytherapy. How dose actually falls off with distance from the source in tissue. This is where the physics of photon and electron interaction with tissue really matters. And it is definitely not always just simple inverse square law.
Okay, this sounds important. This is where that difference between high and low energy sources really comes into play, right? And it's fundamental for knowing why we pick certain sources for certain jobs.
Exactly. Let's first look at the high-energy sources again. Radium-192, Cesium-137, Cobalt-60.
Okay. When you put those sources in a scattering medium like water or tissue, what happens? Photons interact, right? Compton scattering, maybe some photoelectric pair production if the energy's high enough.
Right. And as the distance from the source increases, two things happen. The number of photons passing through a given area decreases just because they're spreading out. That's the inverse square law.
Okay.
But they also decrease because they interact and get removed from the beam. That's attenuation.
Okay, geometric spreading and attenuation both reduce the dose.
Yes, but interactions like Compton scattering also produce secondary electrons and scattered photons. These secondary particles themselves deposit dose further away from the primary source. We call this scatter buildup.
Ah, so scatter adds dose back in, complicating things.
It does. But here's the key point for high-energy sources. Within the first few centimeters, say up to 5 centimeters or so from the source in tissue, the effects of primary photon attenuation and secondary scatter buildup roughly compensate for each other. One takes away dose, the other adds it back.
They kind of cancel each other out near the source?
Approximately, yes. Therefore, in this clinically relevant region close to the source, the net effect is that the dose fall-off is predominantly governed by the inverse square law. So the dose rate falls off approximately as 1 divided by r squared for distances r away. We can often approximate the source as a point or line just undergoing geometric fall-off, modified slightly by this balance.
Okay, so high energy near the source, approximately 108.2 fall off in tissue because attenuation and scatter are roughly balanced.
Got it. Now, contrast this dramatically with the low-energy sources, iodine-125, palladium-103, cesium-131.
Right, these have energies below 50 kilo-electron volts. What happens with them?
Here, the low-energy photons undergo significant photoelectric absorption in tissue. This is the dominant interaction mechanism at these energies in materials like soft tissue made of oxygen, carbon, etc. Remember that probability for photoelectric effect. It's strongly dependent on the atomic number, Z, of the absorber and the photon energy, E. It goes roughly as Z cubed divided by E cubed.
Z cubed over E cubed. Okay, so low E really boosts the probability.
Hugely. Because tissue has elements with relatively higher Z than just hydrogen, and the photon energy E is very low, tens of kilo-electron volts, this photoelectric absorption is extremely probable. It's highly effective at removing these photons from the beam, absorbing their energy locally. And this absorption is in addition to the inverse square law spreading.
Ah, so you have geometry plus this massive absorption effect. What does that do to the fall-off?
The practical consequence, their dose fall-off is much, much steeper than 1 divided by r squared. We're not talking just a little bit steeper, it drops off dramatically.
Like way faster.
Way faster. For example, the dose rate from an iodine-125 seed might decrease by a factor of, say, 5 or even 10 over just a couple of centimeters beyond the reference point. Whereas a high-energy source might only drop by a factor of 2 or 3 over that same distance due to its roughly 1r2 fall-off.
Wow, that's a huge difference.
It's critical. So to reiterate this crucial point, definitely for boards, near the source, high-energy source fall-off in tissue is approximately 1 divided by r squared because attenuation and scatter are somewhat balanced. Low-energy source fall-off is much greater than 1 divided by r squared due to that significant photoelectric absorption.
And that rapid fall-off for low-energy sources is the fundamental reason they work so well for permanent implants like prostate seeds. You get that incredibly steep dose gradient, high dose to the target, rapid drop-off to spare the neighbors.
Exactly, that's the core principle.
Okay. What about shielding those beta emitters? You mentioned yttrium-90.
Right, a quick but important practical point on shielding pure beta emitters like yttrium-90. Remember, betas are high-energy electrons.
Okay, so if you need to shield them, what material do you use? Is it lead, like for photons?
Counterintuitively, no. If you're used to thinking about photon shielding with lead, this is different. You should use low Z material.
Low atomic number material, like plastic.
Exactly. Materials with low atomic number like plastic polymers, lucite, plexiglass, things like that are preferred. Here's why. When high-energy electrons slam into a material and stop, they can interact with the atomic nuclei and produce X-rays. This process is called bremsstrahlung.
Bremsstrahlung, breaking radiation, right?
Right. And the probability of producing bremsstrahlung is proportional to z squared of the stopping material.
Z squared, so high Z material makes lots of bremsstrahlung.
A lot more. So if you use high Z material like lead to stop energetic betas, you'll cause significant bremsstrahlung X-ray production. And these bremsstrahlung X-rays are photons, they can be quite penetrating, and they create an unnecessary and potentially significant penetrating radiation hazard outside the shield you intended just for the betas.
So you stop the betas but create penetrating X-rays instead. Not good.
Not good at all. Using low Z material minimizes this bremsstrahlung production. The electrons primarily lose their energy through ionization and excitation of the low Z material's atoms, rather than radiating it away as X-rays.
Okay, that makes sense. So remember, shield betas with LOWZ material like plastic to minimize unwanted bremsstrahlung X-rays. That's a key practical point.
Definitely a key point.
Okay, so we've met the sources, we understand their key properties, half-life, energy, and crucially, how their energy dictates their dose fall-off in tissue. But how do we actually quantify how strong a specific source is? How do we measure its output in a way that's standardized and useful for calculating the dose clinically?
Right, this is another critical piece. And this concept has actually evolved quite a bit over the history of brachytherapy. We've moved towards more physically accurate and directly measurable quantities. You'll encounter a few concepts, some historical, some current standard.
Okay, what's the most basic measure?
Well, the most fundamental measure of radioactivity itself is activity A.
Activity. That's just the decay rate, right? Disintegrations per second.
Exactly. The number of nuclear decays happening per unit time is measured in the traditional unit of Curies, C, or the SI unit, becquerels, BQ. 1 Curie is 3.7 times 10 to the 10th becquerels.
Okay, but what's the problem using activity directly for brachytherapy sources?
The main challenge is that it's really hard to measure accurately for a seal brachytherapy source, because the radiation that actually leaves the source and can contribute to patient dose isn't just proportional to the internal activity. It's filtered and attenuated by the source's encapsulation material, the metal casing, the wells, everything. The clinically relevant output is modified by the source construction.
So the activity inside isn't what gets out.
Pretty much. So historically, the concept of the exposure rate constant, gamma, was widely used, especially back in the radium days.
Exposure at constant gamma. Okay, how did that work?
It tried to relate the activity of a source to the exposure rate measured in röntgens per hour that it produces at a specific reference distance, usually per unit activity, like per millicurie or sometimes per milligram of radium equivalent.
Okay, so it linked activity to exposure at a distance.
Yeah, the classic example is for radium-226 behind that standard half-millimeter platinum iridium filter. Its gamma constant is about 8.85 Roentgen centimeter squared per milligram hour. Some older texts might say 8.25, but 8.85 is the modern value.
Got it. But what was the issue with gamma?
Importantly, the gamma value depends not only on the isotope itself, but also critically on the source construction, that encapsulation material and thickness. Because it depends on manufacturing details, it wasn't ideal as a truly universal, directly measurable quantity of the clinically relevant output. Different manufacturers' sources of the same isotope could have different gamma values.
Okay, so still tied too much to the specific source design.
Exactly. Building on that, another older concept, largely historical now, but you'll definitely see it in old plans or literature, maybe boards, is milligram radium equivalent. Milligram radium equivalent. So comparing everything back to radium. Pretty much, it compared the exposure rate of any source to that of 1 milligram of radium-226, filtered by that half millimeter of platinum iridium measured at 1 centimeter.
Okay.
So a source with a strength of 1 mgReq produces the same exposure rate as 1 milligram of filtered radium at the same distance, that 8.85 Roentgens per hour at 1 centimeter. You could convert between millicuries and mgReq using the ratio of their gamma constants, but again, it relied on the gamma constant and it had all its limitations, generally not used for modern sources.
All right, so activity, gamma, mgRuq all had issues, which brings us to the modern standard.
Yes, the modern standard and universally recommended quantity for specifying brachytherapy source strength today is air Kerma strength, SK, S sub K.
Air Kerma strength, SK. This is the one recommended by AAPM and Estro, right?
Exactly. It's the standard. Its definition is precise and grounded in fundamental physics. It's defined as the air Kerma rate, K dot air, due to photons with energy greater than some cutoff delta, usually 5 kiloelectron volts, measured at a reference distance d, usually 1 meter, in a vacuum, multiplied by that distance squared.
Okay, let me process that. Air Kerma rate times distance squared. measured in vacuum. Y distance squared.
The formula is skk.air d d2. That distance squared factor mathematically removes the inverse square law dependence from the definition itself. It makes Sk a measure of the source's inherent photon output rate projected to that distance, independent of the 1 or 2 fall-off. It characterizes the source itself.
Ah, okay, so it takes out the geometry part.
In the units.
The standard units for air Kerma strength are microgray meters squared per hour. This unit is often abbreviated simply as U. So 1 U equals 1 microgray meter squared per hour.
1 U. Okay. This is the unit we see on source calibration certificates from the manufacturer or calibration lab, and what we put into the treatment planning system. Exactly. That's the number. So why is SK the preferred standard? Why is it better than activity or MGAEQ?
It must have some key advantages.
It does. Several critical ones. First, and crucially, it's directly measurable using calibrated ionization chambers under standard conditions, usually free in air at a standard distance. Makes it practical and verifiable.
Okay, measurable. Good start.
Second, it's traceable to national primary standards maintained at metrology labs like NIST in the U.S. or equivalent labs worldwide. This ensures consistency and accuracy in source strength specification across different manufacturers, calibration labs, and clinics.
Traceable. Also very important for consistency.
Third, it's relatively independent of the specific source construction details in terms of how it's measured. Because it's measured at a distance, the measurement inherently includes the effects of the source's encapsulation filtration. It directly quantifies the photon output of the sealed source package as it would actually reach the patient, rather than trying to infer some internal activity. It measures the effective output.
Okay, so it reflects what actually gets out of the source.
Yes. And finally, as we're about to see, it provides the perfect starting point and relates directly to the dose rate in tissue through the factors defined in the TG43 formalism. It feeds right into the dose calculation.
Got it. So for boards, for practice, for everything modern, the key is air Kerma strength, SK in units of U. That's the value we use.
That's the one, SK in U. All right, let's move to the absolute core of brachytherapy physics calculation. TG43 formalism, TG43. As we've hinted, calculating the dose rate around real brachytherapy sources in tissue is way more complex than just assuming inverse square law in a vacuum.
Right. Sources aren't perfect points. They have capsules that filter the radiation differently depending on the angle. And the patient's tissue isn't a vacuum. It absorbs and scatters the radiation all over the place.
Exactly. We need a standardized framework that accounts for all these complexities. The source's actual physical geometry, is it a line, a point, how long is it? The attenuation and scatter effects of its encapsulation, and how the radiation interacts within the patient's tissue. And for TG43, we approximate that tissue as a uniform water medium.
We use water as a stand-in for tissue, right? Because soft tissue is mostly water, and the radiation interaction properties are very similar, especially for the photon energies we use in brachytherapy.
Precisely. The AEPM TG43 report, published back in 1995, and its important update, TG43U1, U for Update 1, from 2004, provide the standard two-dimensional dose calculation framework used by pretty much all commercial brachytherapy treatment planning systems today.
And this framework, it's based on actual measurements and sophisticated computer simulations.
Yes, based on extensive high-quality measurements and detailed Monte Carlo simulations performed specifically in water to derive the necessary parameters for all the different source models out there.
Okay, so the ultimate goal of TG43 is to figure out the dose rate, dose per unit time at any specific point in the volume around the source.
That's the goal. Determine the dose rate accurately anywhere. We typically define the point of interest using polar coordinates relative to the source center. R is the radial distance from the source center, and theta, the Greek letter, is the angle relative to the source's long axis.
Okay, R and theta. And by convention, theta equals 90 degrees is the transverse plane, perpendicular to the source.
Correct. Theta equals 90 degrees is the transverse plane passing through the source center. And that's typically where the dose rate is highest in the sideways direction for a linear source, because you have light self-filtration through the source ends.
Got it. So what's the magic formula?
The fundamental equation in the TG43 formalism for calculating the dose rate, D with a dot over for eta, at a point defined by R and theta is.
Okay, lay it on me.
D dot R theta equals SK times lambda times GR theta times GR times FR theta. Whoa! Okay, D dot equals SK times lambda times G over G0 times G of R times F of R theta. Let's break that down meticulously, piece by piece.
Let's do it. They build on each other logically, each accounting for a different physical effect.
Okay, first term, SK, We just covered that. That's our starting point, the air current strength of the source in units of U, microgray meter squared per hour. It quantifies the source's basic output rate in air.
Correct. Next, lambda, the Greek letter lambda. This is the dose rate constant. Its units are typically centigrade per hour per U, CGI-HU.
Dose rate constant, lambda. Okay, what's its job? Its purpose?
Its purpose is absolutely crucial. It converts the source strength, SK, which, remember, is defined in terms of air current rate at a distance in vacuum, into the dose rate to water at a specific reference point.
The air-to-water conversion.
Yeah.
But only at one specific point.
Exactly. By convention in TG43, that reference point is 1 centimeter away from the source center, located on the transverse axis. So R0 equals 1 centimeter and theta 0 equals 90 degrees.
Okay, 1 centimeter on the side. Lambda is essentially the critical air current to dose in water conversion factor, evaluated specifically at that 1 centimeter 90-degree reference point. It accounts for how radiation energy is absorbed and scattered differently in water compared to vacuum, right at that spot. Its value depends on the source's energy spectrum, which is influenced by the isotope and its encapsulation. It bridges the gap from SK to dose rate in water anchored at the reference point.
Got it. SK gets us started. Lambda gets us to dose rate and water at the reference point. What's next? The G terms.
Right. GR theta. This is the geometry factor. Its units are inverse distance squared, like CMOH.
Geometry factor, G. What does it describe?
This factor accounts only for how the dose rate changes purely due to the source's geometric shape and the inverse square law spreading effect, assuming there is no medium, no water, no absorption, no scatter. It's a purely geometric calculation based on how the radioactivity is distributed within the source.
Okay, geometry only. Like in a vacuum, how does it work?
Well, for the simplest case, if we approximate the source as a perfect point source, then GR theta is simply 1 divided by R squared. That's your classic inverse square law fall-off. Radiation spreads spherically.
Makes sense. But most brachy sources aren't points, right? They're like little wires or seeds. They have length.
Exactly. So for a line source approximation, modeling a source with active length L, the formula for G gets more complex. It involves an integral, but the analytical solution is GR theta equals beta, LR sin theta, where beta is the angle subtended by the line source ends at the point R theta.
Okay, a more complicated formula for a line. But what's the practical implication? You mentioned something interesting about this earlier.
Yes. Here's where it gets really interesting, and this is a classic point for boards and understanding dose distributions. A key implication of the line source geometry factor is its behavior close to the source, especially along that transverse bisector where theta equals 90 degrees. In this close-in region, the geometry factor G, and thus the dose rate fall-off purely due to geometric spreading, falls off approximately as 1 divided by R, not 1 divided by R squared.
1 over R, close to a line source. Why?
Think about it. If you divide the line into tiny point sources when you're very close to the line, the point you're interested in receives significant contributions from many nearby points along that line. As you move radially away by a small amount, the distance to each of those contributing points doesn't change proportionally as much as it would from a single point source. The integration smooths it out, leading to an approximate more R dependence for the geometric part.
Ah, okay. Summing up contributions along the line makes it less sensitive to distance close up.
Right. Now, further away from the line source, when the distance R is much larger than the source length L, RL, the line source starts to look more like a point source from afar, and the geometric fall-off transitions back towards being closer to 1 divided by R squared. But the key takeaway is, close up, a line source geometry factor goes approximately as 1 divided by R along the transverse axis. This is just the geometry part, remember.
Got it. Line source, close up, transverse plane, geometry factor 1R. Okay. What about the G0 in the denominator? Yeah. GR0, the D0.
GR00 is simply the geometry factor evaluated at the reference point. R0 will equals 1 centimeter, the D0 equals 90 degrees.
So why divide by it?
Its purpose in the formula is purely for normalization. By dividing GR theta by GR0, the entire geometry term in the square brackets becomes equal to exactly 1.0 right at the reference point.
Ah, it sets the geometric baseline to 1.0 at the reference point.
Exactly. It allows the other factors, G and F, to then represent corrections relative to this normalized geometric baseline starting at the reference point.
Clever. Okay, so we have SK, lambda gets us to dose rate at the rest point, GG0 scales that based on geometry. What's next? GOR.
Yes, GR. This is the radial dose function, and it's unitless.
Radial dose function, G of R.
Okay, this must be where the water medium comes back in.
Precisely. This function corrects for the combined effects of absorption and scatter in the medium water. specifically evaluated along the transverse axis, i.e. at theta equals 90 degrees, relative to what you would expect just from the geometry factor g alone in a vacuum.
So it accounts for the fact that water is an empty space. It absorbs and scatters.
Exactly. It quantifies how much the actual dose rate along the transverse axis deviates from the purely geometric falloff because of interactions in the water. It's also normalized, so GRO equals 1.0 at the reference radius R0 equals 1 centimeter.
Okay. How does GR behave? Does it depend on the source energy? Hugely dependent on the source energy spectrum. For high-energy sources like iridium-192, remember how attenuation and scatter roughly balanced near the source? That means GOR might be slightly greater than 1.0, within a millimeter or two, due to scatter buildup initially winning. Then further out, it decreases and becomes less than 1.0 as attenuation eventually dominates scatter.
Okay, slight bump, then decrease for high energy. What about low energy?
For low-energy sources like iodine-125 or palladium-103, remember that massive photoelectric absorption? This causes GR to fall off very rapidly with increasing distance r beyond the reference point. It plummets much faster than for high-energy sources.
Right, because the water is just gobbling up those low-energy photons.
Exactly. So the reason GR is so different for high versus low energy sources directly reflects the energy dependence of photon interactions in water. Compton and pair production dominate high energies, scatter buildup, then attenuation. Photoelectric absorption dominates low energies, rapid attenuation. The shape of the GR curve is a direct signature of these physics interactions in the medium.
Makes sense. Okay, one factor left. FR theta.
Last one, FR theta. This is the 2D anisotropy function, also unitless.
Anisotropy function. Okay, GR handled medium effects along the transverse axis. Theta 90, does F handle stuff off that axis?
Precisely. FR theta accounts for dose variations off the transverse axis, meaning at points where theta is not equal to 90 degrees. These variations mean the dose distribution isn't perfectly symmetric around the source. It's anisotropic, meaning direction dependent.
And what causes these off-axis variations? Why isn't the dose the same all around at the same distance?
They primarily arise from photon absorption and scatter happening within the source itself, within the radioactive material distribution, and very significantly within the source's encapsulation. Think about a linear source like a seed or wire.
Okay.
Photons trying to exit straight out the ends of the source often have to pass through more capsule material, maybe weld spots or thicker end caps, compared to photons exiting straight out the side on the transverse axis.
More self-filtration through the ends.
Exactly. This differential filtration and also scatter within the source package itself causes the dose rate to generally be lower off the ends compared to the sides, even at the same radial distance r.
Okay. And how is F normalized?
The anisotropy function F is normalized so that FR, 90 degrees, equals 1.0 at all distances r. So it makes no correction on the transverse axis itself. That's where GR takes care of the radial medium effects. For angles off the transverse axis, theta and 90 degrees, FR theta is typically less than 1.0, reflecting that reduced dose in those directions.
And this F function is why the isotopes lines around linear sources aren't perfect circles or cylinders. They get squashed at the ends.
Exactly. The reduced dose off the ends, quantified by FR theta being less than 1, causes the isotopes lines to be compressed or squashed along the source axis relative to the transverse plane. This often results in that characteristic butterfly shape or peanut shape you see on treatment plans, especially for longer sources.
Got it. And where does the data for F come from? It sounds complicated.
It is quite complex. The values for FR theta are typically obtained from published along and away tables, which list F values for various R and theta points, or from complex data sets derived from very detailed measurements or Monte Carlo simulations specific to a particular source model and manufacturer. It's very source specific. So let's just quickly put it all back together conceptually. The TG43 formula is like a step-by-step recipe to calculate dose rate.
Okay, walk me through it one last time.
You start with the source's fundamental output strength, the air Kerma strength, SK, measured in air.
Step 1, source strength.
Lambda then converts that SK value into the expected dose rate in water right at the standard reference point, 1 centimeter 90 degrees.
Step 2, convert to dose rate in water at the ref point.
The normalized geometry term, GG0, then scales that reference dose rate based purely on the source's shape and geometric spreading, 1R, 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 ignoring the water medium, gets you dose rate based on geometry alone relative to the ref point.
Step 3, scale for geometry.
The radial dose function, GR, then corrects that geometrically scaled dose, for the effects of absorption and scatter happening in the water medium as the radiation travels outwards along the transverse axis.
Step 4. Correct for water effects radially on transverse.
And finally, the anisotropy function FRR theta applies a further correction for the angular variation in dose caused by absorption and scatter within the source itself and its encapsulation, adjusting the dose rate for points that are off the transverse axis.
Step 5. Correct for angular variations due to source capsule. Perfect.
And the critical thing to remember, really hammer this home, the factors lambda, GR, and FR theta are not universal constants. They are highly specific to each individual source model and each manufacturer.
Right. You can't just grab the data for one company's iridium source and use it for another company's, even if it's the same isotope.
Absolutely not. You must get these parameters from reliable published data specific to the exact source model number and manufacturer you are using clinically. This data usually comes from the treatment planning system TPS vendor, who licenses it, or from peer-reviewed literature and AAPM task group reports. Using the wrong data is a recipe for incorrect dose calculation and potential errors.
Okay. That's a really important practical point. Use the right data for your specific source. So understanding these sources, their properties, and really getting into the weeds of the TG43 formalism, it's crucial for several reasons that go way beyond just passing physics boards, right? It directly impacts clinical practice and patient safety.
Absolutely. First, it profoundly impacts source selection and clinical rationale. Knowing the half-life, average energy, and especially that dose fall-off characteristic, is it roughly 102 or much steeper, directly informs your clinical decisions.
Yeah, like choosing between iodine 125 and palladium 103 for prostate seeds. It's not random. You're trading off half-life, which affects dose rate, against average energy, which affects penetration and sparing.
Exactly. Or deciding to use iridium 192 for HDR. That allows rapid treatment, outpatient procedures, dynamic planning. But it comes with the need for serious shielding and rigorous QA because of the high activity involved.
Right. Second reason.
It's essential for interpreting and critically evaluating dose distributions. When you look at a treatment plan, why do those isodose lines look like peanuts around an iridium wire?
Because of the anisotropy function,
Absolutely.
SR, theta, lower dose off the ends due to filtration.
Exactly. Or why does the dose fall off so much faster than 1 or 2 for an iodine seed a few centimeters away?
Because of the radial dose function, GR. Photoelectric absorption just kills the dose at low energies.
Right. Understanding TG43 gives you the fundamental physics insight to look at those dose distributions and ask, does this make physical sense given the sources and the geometry? You can evaluate the plan critically.
Okay. Super important for plan evaluation. Third reason.
It underscores the accuracy requirements and sensitivity of dose calculations. TG43 relies heavily on accurate input data, SK, lambda, GF, and also on precise digitization of where the sources are, where the applicators are, where the anatomy is.
And because brachytherapy has such steep dose gradients, especially near the source or critical organs.
Exactly. Even small errors in that input data or source positions or applicator localization can lead to clinically significant dose discrepancies. Too much dose here, too little dose there. That's why rigorous quality assurance of the TPS, the source data, the source applicator localization images, it's all absolutely vital. The margins for error are small.
Very true. Okay, and finally.
Finally, it's important to be aware of the limitations of standard TG43. The standard formalism we've described assumes the sources are sitting in a uniform, infinite water bath.
Which the patient isn't, really.
Right. It doesn't inherently account for tissue inhomogeneities like dense bone or air cavities in the rectum or bladder or lung tissue. These all have different absorption and scattering properties compared to water.
Okay. What else does it miss?
It also doesn't fully account for the shielding effect one source might have on another nearby source. We call that inter-source shielding. Or the attenuation and scatter caused by complex high-Z applicators themselves, like stainless steel tandems and ovoids in GYN brachy.
Ah, so it simplifies the situation quite a bit.
It does. It's a very good model, the standard, but it has assumptions. For higher accuracy in really complex situations, significant inhomogeneities, complex applicators, more advanced dose calculation algorithms are needed. These are generally called model-based dose calculation, MBDC, algorithms.
Model-based, like using Monte Carlo or other transport methods.
Exactly. They try to model the physics more directly in the actual patient geometry. While TG43 is the workhorse and the current standard you need to know inside out, it's good to be aware of its limitations and that these more advanced MBDC methods exist for specific complex cases. All right, before we hit the board questions, let's crystallize this. Let's pull out a few essential, high-yield clinical pearls based on everything we've discussed. These are the absolute must-remember points for your exams and for guiding your clinical thinking day-to-day in brachytherapy.
Okay, lay them on me. Pearl number one.
Know your source is cold. You have got to be intimately familiar with the key properties of the most common isotopes. That means iridium-192 for HDR, TS 74 days, AVGER, 380 kilo electron volts.
Got it. Iridium, 74 days, 380 kilo electron volts. And for LDR seeds?
For LDR permanent seeds, iodine-125, TN 60 days, AVG-EVAN 28 kilo electron volts, and palladium-103, TS 17 days, AVE-21 kilo electron volts.
Iodine, 60 days, 28 kilo electron volts. Palladium, 17 days, 21 kilo electron volts. Okay. And the differences in half-life and energy drive their clinical use.
Absolutely. Half-life dictates dose rate kinetics, energy dictates penetration and fall-off. That's why you choose one over the other.
Okay. Pearl number two.
Understand the crucial dose fall-off distinction. This is fundamental physics with huge clinical relevance. High-energy sources, like iridium, primarily follow approximately 1 divided by r squared fall-off near the source in tissue because attenuation and scatter roughly balance.
High energy or 10-1R. Got it.
Low-energy sources, like iodine or palladium, have a fall-off that is much, much steeper than 1 divided by r squared due to the overwhelming effect of photoelectric absorption in tissue at those low energies.
Low energy 1R ready.
Okay.
And that rapid fall-off is the key advantage for sparing OARs in permanent implants.
Exactly. Oh, and also part of this pearl. Remember, shielding pure beta emitters requires LWZ material like plastic to minimize bremsstrahlung.
Right. Low Z for betas. Okay, pearl number three.
Know how source strength is specified. The modern standard recommended quantity used everywhere now is air Kerma strength, SK, measured in units of U, microgray meter squared per hour.
SK in U, because it's measurable, traceable, and reflects the actual output, including encapsulation effects. Forget activity or MGRAQ for modern calculations.
You got it. And pearl number four.
The TG43 factors.
Be able to name and describe the purpose of the 5 key factors in the TG43 dose calculation formula. Dose rate, SK, lambda, AG0, A0, HA, RRA, theta. You need to know what each symbol represents and why it's in the equation.
Okay. SK, source strength. Lambda, dose rate constant air-to-water conversion at ref point. G, geometry factor, pure geometric 1RR or 1R effect, GR, radial dose function, medium absorption scatter on transverse axis, and FR theta, anisotropy function off-axis variations from source capsule.
Perfect. If you know those 4 pearls, you've got a really solid handle on the core physics principles.
You know, that TG43 formula, even broken down, can be a bit abstract. Let's maybe try an analogy to make it stick better. Help visualize what each factor is actually doing.
That's a great idea. Analogies can really help solidify these complex physics concepts. Thinking of it like, okay, imagine you're holding a special kind of light source. Maybe it's not a bulb, but like a miniature light tube, kind of like a tiny fluorescent bulb. That's your brachytherapy source.
Okay, a mini light tube.
And you're standing in a room filled with really dense uniform fog. The fog represents the patient's tissue, our water phantom. You want to figure out how bright the light is, that's our dose rate, at different points in this foggy room.
Okay, light tube, foggy room, brightness is dose rate. I'm with you.
All right. SK, the air Kerma strength, is like knowing the absolute total light output power of your specific light tube, measured in a vacuum, like on the factory spec sheet, before you even bring it into the fog. It's the raw, inherent output power of your source.
Got it. The bulb's rated power, independent of the fog.
Lambda, the dose rate constant, is like a specific conversion factor. It tells you how much usable brightness you actually get in that specific foggy room, water, right at a standard defined spot, let's say 1 meter directly off to the side of the middle of the tube. It converts the tube's raw output power, SK, into effective brightness in the fog, but only at that one reference point. It accounts for the initial impact of the fog right there.
So it's the vacuum to foggy room brightness conversion, but specifically anchored at that one reference spot. Like how much brightness you get for the power you put in right there.
Exactly, at that reference spot. Now, the geometric term, G divided by G0, the normalized geometry factor, this is like how the brightness changes purely based on the shape of your light source. Is it a tiny point or a long tube? And how the light spreads out geometrically as you move away from it, if there were no fog at all.
Okay, just the spreading effect.
Yeah. For a tiny point bulb, light spreads spherically, brightness drops as 1 over r squared. For our light tube, remember, close up, it might spread more cylindrically, and the light intensity falls off slower, maybe like 1 over r, just due to geometry. This factor numbs the fog completely.
Okay, so GG0 is just the geometric spreading pattern, normalized at the reference point, pretending the fog isn't there.
Precisely. Then comes GR, the radial dose function. This is like the effect of the fog itself absorbing and scattering the light, specifically as you move radially away from the source, straight out sideways along that transverse axis. The further the light has to travel through the fog, the dimmer it gets, because the fog absorbs and scatters it.
Ah, so GRR is the fog's dimming effect as you move straight away from the tube.
Right. It corrects the brightness you calculated just from geometry for the additional loss of light due to absorption and scatter in the medium as distance r increases radially compared to what you'd expect in empty space. And for really dense fog-like tissue for low-energy photons, this dimming effect, this GR, drops off really fast.
Okay, GR equals fog dimming radially. Got it.
What about F?
Finally, FR theta, the 2D anisotropy function. This is like the effect of the flashlight's casing, or the light tube's own structure. Our light tube isn't just raw glowing gas. It has a glass tube around it, maybe metal end caps.
Right, the source itself isn't perfectly uniform.
Exactly. If you look directly at the side, theta equals 90 degrees, maybe you get the maximum brightness, F1. But if you look more towards the ends of the tube, theta closer to 0 or 180 degrees, the metal end caps, or the way the glass is sealed, might block some light or make you look through more glass, making it dimmer in those directions, F1.
That makes perfect sense. F accounts for how the source's own physical construction, its own bits and pieces, affects the light distribution in different directions, making it not perfectly uniform or isotropic.
Exactly. So putting the analogy all together, brightness, dose rate, raw bulb power, SK, times fog conversion factor at reference lambda, times geometric spreading pattern, GGA0, times how fog dims light radially, times I, times how the bulb casing dims light at angles, FR theta.
That's a great analogy. Bulb power, fog conversion, geometry spread, fog dimming, casing dimming. That really helps visualize what each piece of that formula is doing. Thanks.
Now, remembering the order of those factors in the formula, SK, lambda, GG0, GF, can be tricky under pressure. So here's a little mnemonic I came up with back when I was studying for boards. Might help.
Oh, I love a good mnemonic. Absolutely essential for board review, especially for lists and formulas like this. Yes, please. Lay it on us.
Okay, so the formula again is D dot is SK, SK, S, lambda, S, G0, AGR, FS, a theta. To remember the sequence and maybe jog your memory on what SK, lambda, G, G0, G, and F stand for, you can use this phrase. Some lovely girls give radiation factors.
Some lovely girls give radiation factors. That's fantastic and wonderfully memorable. Let's see. S for SK, source strength. L for lambda, dose rate constant. The first G for G, geometry factor. The second G helps remember G0, the reference geometry factor for normalization. R for the radial dose function, GR. And F for the anisotropy function, F. That should definitely help cement the terms and their order. That's a keeper. Thanks for sharing that one. All right, feeling ready for a quick board blitz? Let's test your understanding of these core concepts with a few multiple-choice questions. These are definitely the types of questions you might see, hitting the key distinctions.
Let's do it. Bring on the questions. Hopefully that analogy and mnemonic helped. Let's see if we've successfully navigated the TG43 fog.
Okay, question 1. The radial dose function, G of R, in the TG43 formalism primarily accounts for A. The change in dose rate due solely to the inverse square law. B. The variation in dose rate off the transverse axis compared to on the transverse axis. C. The combined effects of absorption and scatter in the medium along the transverse axis relative to geometric falloff. Or D. The conversion factor from air Kerma strength to dose rate in water at the reference point.
Okay. GR. That's the radial part. In the medium along the transverse axis.
Yeah.
Relative to geometry. So I'm going with C.
C is correct. Explanation. Option C precisely describes the purpose of GR. It corrects for how the dose along the transverse axis deviates from pure geometric falloff due to attenuation and scatter in the medium. Option A is G, option B is F, option D is lambda, so C nails GR.
Shoo. Okay, next.
Question 2. Comparing dose calculation for an iodine-1 25 seed, average EA 28 kilo electron volts, versus an iridium-1 92 source, average EA 380 kilo electron volts, using TG43. Which factor would be expected to show a much more rapid decrease with increasing distance r beyond 1 centimeter? A. Geometry factor, GR, 90 degrees. B. Radial dose function, GR. C. Anisotropy function, FR, 0 degrees. Or D. Dose rate constant, lambda.
Okay, comparing low-energy iodine versus high-energy iridium. Which factor drops off much faster with distance?
Yeah.
That has to be related to the energy deposition in the medium. Low energy gets absorbed much faster. That was GR. So I'll go with B.
B is the correct answer. Explanation. This tests the energy dependence of GR. For low-energy iodine, photoelectric absorption is huge, making GR decrease very rapidly with distance. For high-energy iridium, attenuation scatter are more balanced near the source, so GR changes much less dramatically initially. G is geometry, F is angular, lambda is a constant at the ref point, so the rapid radial fall-off difference due to energy is captured by GR.
Good. Makes sense. Keep them coming.
Question 3. The currently recommended quantity for specifying the strength of brachytherapy sources, traceable to national standards and relatively independent of source construction, is A. Activity in curies, CI. B. Milligram radium equivalent, MGREQ. C. Exposure rate constant, gamma. Or D. Air Kerma strength, ST.
The source strength specification. We talked about the evolution. Activity had issues. MGREQ and gamma were historical and construction dependent. The modern standard, traceable, measurable. That's air Kerma strength, SK. So D.
D is absolutely correct. Explanation. Air Kerma strength, SK, in units of U is the quantity recommended by APM and ESTRO. It's directly measurable, traceable, and better reflects the usable photon output compared to the older methods. SK is the standard.
All right, one more.
Last one, question 4. Near a long linear brachytherapy source, for example, an iridium-192 wire, along its transverse bisector, theta false 90 degrees, the dose rate primarily falls off with distance r approximately as A, 1r and r, B, 1r and r, C, 1r, d, constant with no fall-off.
The key words here. Near a long linear source along the transverse bisector. We talked about the geometry factor G for a line source close-up. It wasn't 1R and R. It was approximately 1R, so C.
C is correct. Explanation. This specifically tests the behavior of the line source geometry factor close to the source on the transverse plane. Due to the integration of contributions along the line, the geometric component of the dose fall-off is approximately proportional to 1 in this region. Far away, it behaves like 1R and R, but close up, it's 1R. Well done.
Okay, so just to quickly wrap up and summarize our discussion today on these core brachytherapy physics topics.
Yeah, we really covered a lot of ground. We started by exploring the brachytherapy source zoo, getting familiar with the common isotopes like iridium-192, iodine-125, palladium-103, cesium-137, cobalt-60, and even the beta emitter yttrium-90. We highlighted their key physical properties, energy, half-life, and how those drive their clinical uses.
And we really hammered home that crucial difference in dose fall-off with distance. Remember, high-energy sources fall off approximately as 1 divided by r squared near the source in tissue, attenuation scatter balance. Low-energy sources fall off much faster than 1 divided by r squared due to significant photoelectric absorption. That's a huge takeaway.
Huge. And also, don't forget, shield betas with LOWZ material.
Right. Then we established air Kerma strength, SK, in units of U as the modern, standard, and recommended way to specify source strength, understanding why it's better than the older methods.
SK in U.
And finally, we meticulously dissected the core dose calculation framework, the TG43 formalism. We broke down that key equation. Dose rate SK, lambda, SGG0, X, GR, SSR, theta. And we explained the role of each of those 5 factors. SK, source strength, lambda, dose rate constant, GG0, geometry factor, GR, radial dose function, and FR, theta, anisotropy function. We also touched on the limitations like inhomogeneities and applicator effects and the existence of model-based calculations.
Understanding these physical principles, it's not just academic stuff. It truly is the foundational first step towards being able to safely, accurately, and effectively plan and deliver brachytherapy treatments for your patients. It lets you choose sources wisely, evaluate plans critically, and appreciate the precision needed.
Couldn't agree more.
You know, physics boards, they always loom large, don't they? Trying to keep all these formulas and concepts straight can feel like a real challenge.
Huh? Yeah, tell me about it. Hopefully, digging into TG43 like this makes at least that part feel a bit more manageable. Breaking it down term by term, using the analogy of the mnemonic, it all helps.
Definitely. You know, I heard a joke the other day thinking about trying to remember all this physics stuff after the exam. I'm really hoping my recall of these formulas right after the boards is nothing like a pure beta emitter.
Oh, why is that? What do you mean?
Because I don't want it to have a very short range and produce a lot of Bremsstrahlung when it stops.
That is a top-tier physics joke. Excellent. Let's just hope our listeners' retention has a much longer range than a Y90 beta particle, and maybe avoids any unnecessary scatter during the actual exam. Well, that wraps up our comprehensive discussion today on brachytherapy physics sources, strength specification, and dose calculation using the TG43 formalism.
Understanding these concepts is absolutely essential knowledge for any radiation oncology resident. It's critical for boards, yes, but even more so for the safe practice of clinical brachytherapy.
We've covered the core physics principles today. In our next segment, we'll build directly on this foundation. We'll explore how these different sources are actually used in various clinical applications, getting into specifics of intracavitary, interstitial, permanent seed implants, and then we'll shift focus to the absolutely critical aspects of safety regulations and quality assurance procedures specifically tailored for brachytherapy.
Remember, you can find additional resources, including practice oral board scenarios, specifically for residents, over at radoncSmartLearn.com. That's radoncSmartLearn.com. And be sure to subscribe to RadOnc Smart Review so you don't miss our next installment diving deeper into brachytherapy applications and safety.
Thanks very much for tuning in and investing your time in strengthening your physics knowledge.